Okay, good morning. So it's Tuesday, February, 27th. Yes, okay. So the first thing I'd like to do is update you on a couple of announcements. So deadline for Project 1B remains tomorrow night, right? And I've postponed the deadline for Project 2A until Friday night. So this will give us a little more time, and I would like to address any remaining questions you might have about either of these projects now, preferably. So any questions or, there's one other announcement before we get into this. So because of my busy schedule, I'm afraid I haven't finished grading yet, the test, but I'm planning to finish that between this afternoon and tomorrow morning, so I will keep you posted, okay? So sorry about that delay. And now back to the project. So let me pull up the guiding example for Project 1B so we can address any remaining concerns there. And then the other actual thing I wanted to pull up is the relevant part of, let's see, actually this section here, 321, okay? So any questions about 1B that might be remaining? So just to point this out very clearly, all you should have to do to verify that the SIG pipe handling is in place is, as you saw on the Slack, there was a quick discussion about this, very helpful. You just pipe from your console application into something else that takes only a few lines, let's say fewer than your application produces, and when your application tries to write to the pipe, that the downstream process closes, okay, and your process tries to continue writing. That is an error that your application sees, and it is told, oh, there has been a SIG pipe error. And by handling it in this way, you're setting it up like the standard way to do this in Unix, which means so you're basically registering a handler. This is similar to setting up an event listener in, let's say, an Android app, very similar. Okay, so also kind of an observer pattern where we're registering this observer to the SIG pipe event. So we're just registering that. And if the event occurs later, then the mechanism for handling different possible events says, okay, let's see if there's a handler for SIG pipe. Yes, this one. And it invokes this piece of code, which is a lambda expression or anonymous function. And it says, okay, we have to exit. So it exits cleanly when the SIG pipe occurs, as opposed to trying to work really hard to continue writing to a pipe that's already closed, which is what would have happened, as I demoed in class, if there weren't this kind of handling. So any questions about the SIG pipe? Yes?
My code, but I feel as though maybe it's not in the right location. It still seems to have some sort of error when I type into something else that gives that error, the SIG type error. And so I'm just trying to, I feel like I have no way to problem solve through it because I don't know enough about it.
Oh, okay, yeah, sure. Well. let's address that. So first of all, what exactly are you observing?
The error seems different than other errors I've had because it's not in red. I don't know if that's because.
Well, is it a compile time error? I mean.
I can do it real quick now because I can't remember what.
Oh, okay.
Exactly.
Or we could also look at it. I mean, if you're seeing it, if it ran fine.
Then there was an error.
Okay. I mean, so if you see it in the IDE or when you do a build, then that's a compile time error. If you see it when you're trying to run it, actually, then that's a runtime error.
Okay, it must be a runtime error.
Okay. But you're not sure what it was. Yeah, maybe you can try to do it. But so the key point is the first thing you should do in your main is register this handler so that the handler is in place. So this should be at the very top of your main. Okay. So that is really the key thing. Any other questions about 1B? So I'm assuming you're up to speed on the very helpful discussion we've been having on the Slack. So for example, what kind of refactoring is required? And the reason in 1A we needed the observer pattern, as you can actually see here in this iterator's example, right? The reason you needed the observer pattern here was, of course, because if you just print directly to the standard output, then that's not easy to test, right? So that's why we introduced the observer pattern, made it modular, and basically set up this plug-in point for this do output where we were able to combine the central logic piece, which is this one, with a suitable observer, and we set it up so that we had a choice between the observer for printing, which would give us back the equivalent of the simple version that's not modularized, and the other observer that would accumulate the output data in this buffer that we could then look at as part of testing, right? So that is the key reason we're using the observer pattern in the mutable version, in conjunction with the fact that here we're not returning any result. So this is a method that has, and we can look at the actual interface here, right? So the result type here is unit, right? So it doesn't return a result, it just does something. So what we're seeing is the side effect. The side effect is either stuff shows up in the console output, or it goes into the buffer where we can then observe it later, right? That's what we needed here, because there was no other good way in a mutable style to return something. But the functional style is different in the sense that, so we'll look at the functional version here. Functional style is different in the sense that we're already cleanly separating the central logic from the printing, right? In the other one, the printing was inside the loop, in the imperative one. Here, we produce a result structure, and then only at the very end, all we do is loop over that and produce the results, although it's actually not in terms of time. The timeline, it's not separated like that. In fact, the part in the middle sets up a structure that you're only actually starting to read from the input when you're starting to print the output, because when you're trying to print the first result, what needs to be there? Well, there needs to be a number we would have read. So then it waits here, right? It starts actually going in here only when you start printing, when you try to print the first result item in this structure. And then that means it's now actually going to go in here, and it's only going to get up to this point where it prompts for the first line of input, and it'll continue past that only if the user actually enters something and then hits return, right? So that's the thing. So in other words, what we're setting up here as so-called results is really an iterator that kind of connects the output to the input in such a way that it reads from the input as needed and as input is or becomes available, right? So what this iterate does is, of course, I mean, you know from looking at the API documentation, right? So you look at the iterator companion object, and it says iterate is, so iterate takes a starting value and then a function. And iterate returns the starting value. The first time you say next, right? It'll return the starting value. The second time, it'll return the function applied to the starting value. The third time, it'll apply the function applied to the function applied to the starting value. So, in other words, the first value you get is the starting value, and then subsequent values are generated from the previous value by applying the function one more time. So it's like a loop, but functional, right? So it's just like basically a while true loop, okay? So how do we then convert that into something that terminates at some point? Well, we somehow have to introduce some kind of case distinction that we can detect downstream. What is the upstream condition for terminating here? You can give an answer either looking at it externally or internally. When does this terminate, let's say, from the point of view of the user of this little utility? That's exactly right. Which iterator? Well, the one at the top, right? Because we're reading successive lines, right? So if that one ends because you type the end of file character, then the has next says false, right? And somehow this iterate tries to keep going, but we need to introduce that little wrapper structure so that downstream, meaning like the stuff that we do to that iterator starting value, f of starting value, f of starting value, and so on, right? The basically successive application of the loop body to the previous result. We need to equip that in such a way that downstream we can detect the termination coming in from upstream, basically our standard input. So how do we do this here? Well, we say, so the starting value is an actual value. So when you invoke option with a value, it'll give you a sum. When you invoke option, the factory method, with null, it'll give you a none. Okay. So it's capable of wrapping things nicely, but it'll statically, from a static typing point of view, it's nicer because it types it as option as opposed to the more specific type sum versus none. Okay, so that's why it's nicer here. It's more helpful to say option instead of sum. You could have said sum, but then the typing wouldn't have worked out as nicely. Okay, so what is our f that we apply successively as the loop body? So f is like a functional version of the loop body. So we'll say, well, if we are getting a value, if we had a value in the previous step, then let's see what that value is. Okay, then it matches this. we ignore the actual string value, we take the number, and then we say, well, let's now see if there is another input value. That's what the line has next says, or tells us. So if so, then we'll say, okay, let's grab that next input value, and then we'll say, okay, yes, there is also after this step, there is going to be an updated value, which is the current line, and then n plus the length of the current line. So we're accumulating in that second item of the tuple, we're accumulating the cumulative character count of this input. If there wasn't any more input, then we'll return a none. So in other words, for each input line, we will so the output of the iterate for each input line, well, it'll start with dummy and 0. Okay? And then for each input line, it'll return a value sum, so option sum, that line plus the accumulated character count. But if the input runs out, from that point on, f will always return none. So we'll get, for example, if we enter hello world, what up, it'll say hello, or some hello and 5, then it'll say world, and then 10, and so on, right? And then after up, it'll just say none, 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 infinitely many times. That's how the iterator behaves up to here. Any questions so far? Yes?
So for case, what is the underscore?
Oh, yeah, okay. So the underscore in a pattern, right, so in a match case pattern, is basically a placeholder for a piece of the structure you're matching to this pattern that you don't really care about. So it'll match any structure that could be there, and the underscore is just like an anonymous variable name because you're not interested in using that in the body of the case. Okay. Whereas the n, which is the character count accumulated so far, that one we need because we're going to add the length of the current line to that, right? So then we're returning basically option or sum, the current line and the updated character count. And when that goes back in here, we're ignoring that line again. So the underscore would match this one, and we don't really care about that because we already echoed it here. So then for calculating the next character count, we don't need the old line anymore. So that's why we're ignoring that. That's the old line coming in. But we need the old character count, and then we'll update that and return the new line and then the new character count. And it keeps going like that. But when we run out of input lines, the has next will be false, and we'll go into else. And it'll keep going, and every time it'll say none, infinitely many times. Does that make sense? Okay. Other questions about this part? So, okay. So now we still have this problem. We ran out of the input, and the iterate keeps going infinitely many times. So now we need to keep control of the iterate. What do we need to do? First of all, the first value it produces is dummy 0, right? Sometimes. What do we want to do? Well, we want to get rid of that dummy, right? That's only there to get the thing started. Really, we're interested in the 0, but not the dummy string, right? We could have put any value there, and it ignores it anyway. We just needed the 0 to come in here as the very first value of n. Okay? So we're ignoring the dummy 0 value, and then we'll say, well, let's now take a finite prefix. So on the worksheet, you've familiarized yourselves with take and then some numeric value. That'll take the finite prefix of the specified length. So you might have an infinite iterator. You did the worksheet for sequence structures, which are always finite, right? So here we're just kind of dealing with potentially infinite computations or sequences. That's what the iterator can represent. And then we are looking at applying the same techniques to get finite prefixes of that potentially infinite structure. Okay, so if we had an infinite iterator and we said take 5, it would take the first 5 items of that iterator. And then after that, we wouldn't pull any more values from the iterator, so the iterator wouldn't keep going. And the point of an iterator is that it keeps working only as you're pulling items by invoking next. If you don't say next, the iterator is just sitting there, not eagerly producing things. So it only produces things as you pull them from the iterator. Okay? So in that sense, it's the opposite, or the kind of the counterpart to an observer. Right? So iterator allows you to pull values as you need them. Observer doesn't do anything until you actually push values to it. And then as it receives the values you're pushing, it'll process the values. So that's why they're kind of duals of each other. And that understanding is kind of like switching from iterator to observer is the whole conceptual foundation of all of this reactive programming stuff that you hear about in discussions, right? So reactive means switching from a pull model, where you're pulling from iterator, like in this loop, to a push model where you have an observer that you push to. So in that respect, the imperative version is more reactive. That do output thing means, it's reacting to output events. So that piece at the end is the reactive piece. And the events are, well, a line showing up on the input and being entered into the system. But so here we're looking at it functionally, representing everything as an iterator, including the result. Okay. So back to the take while. So take 5 or take some number means you're taking that many or up to that many items from the sequence or iterator. And after that, you're leaving it alone. You're leaving the iterator alone, so it won't keep producing further values. So the key thing to understand is that the iterator will produce output values for each line you read and accumulate the length. And after there's no more input, it'll produce an infinite sequence of none values, but it will not just keep doing that. So I'm summarizing what I just said earlier. So it will not keep doing that until you pull from it. Every time you say next, you will get a none. You say next again, you'll get another none. But if you don't talk to it, if you don't say next, it's not going to give you any more values. So it's not a problem that it could have kept going infinitely, right? That's not an issue. That's actually how it's set up. But you control how far you want to go by pulling from it. So that's why now there's another version of take, which says keep taking values until a particular condition is, or as long as a particular condition is met. And by the way, so you've seen the underscore dot, that's just an abbreviation of writing this kind of thing. So if you see underscore dot toInt, it's related to your earlier question. So it's a placeholder in this case because you're taking an argument that you call x, and then the only thing you do with x is invoke one function on it. That's why Scala allows you to abbreviate the presence of that one argument just by underscore. So instead here I could have avoided x arrow x and instead said underscore dot x defined. So that's where that toInt in the other examples comes from. Just a little aside. So the take while means this iterator will keep going only as long as the condition is defined. Well, I mean, as the condition is true. And here the condition we use is whether or not the option value is defined. So if the option is a sum value, that means it's defined. If it's none, it means it's not defined. So in other words, suppose we run out of input, then this iterator starts producing none values, and then the take while says, oh, it's no longer defined. So it stops here. So that means it's kind of like what the SIG pipe is for, right? So except that there isn't a way to push back the termination upstream. Instead, we're representing the termination, or instead we just stop the iteration if some kind of condition has occurred. So effectively, it's the same thing as saying, well, we're not pulling from the upstream anymore. We're just shutting it off. Okay? So the take while is defined as the sequence or iterator consisting only of the values for which the condition is true, meaning this condition or predicate, and it stops at the first item for which the predicate becomes false and ignores any subsequent possible values. Okay. So effectively what this means is if here we have some hello 5, some world 10, some what 14, and so on, and then none, this will give you only the values that are actually some values. And it will stop just before the nones start coming in. So it's only the actually defined values from the option, some string and updated length. Okay? So in other words, here we're getting only the values that come from actual input lines. And now they are still wrapped. So we can actually show this for a second here. Let's see what's going on here. Oh, I see. Okay. Let's see. So, for example, we could say iterator some 5, some 3, some 7, some 2, and then we could provide a bunch of none values like this. Okay. So now it tells us, okay, it's a non-empty iterator of option int. So if we say res0, to see the whole thing, if we say res0 to list, it'll show us all those values, but we're at the end of the iteration, so if we do that again, it won't have anything else to show, right? So if we invoke this again, it'll show an empty list because the to list means we're actually iterating through it, right? You've already seen this kind of thing. So for further experiments, we just have to recreate the iterator. So now, if we say res3 take while and then underscore is defined, that will be only the sums and it'll drop the nones. Okay. And we can see that now if we said res4 to list, but instead we're going to say res4 and then map, because the problem is that the values we want which in this case are the numbers, are still wrapped in an option or in a sum, and we want to get rid of that, we have to say get, because that unwraps the option value if it's defined, right? So we can do this. And now if we say res5 to list, okay, or to sequence, it doesn't matter, then we get, and you can see right here, right? So res4 is an iterator of option int values, right? And res5 is an iterator of the int values. So that wrapping is gone. So we can verify this right here. Okay? So that's what we need to do here. So this is just to unwrap them, to get rid of that sum wrapper. And then we're printing these pairs, which are the current line and the updated character count. Okay? So you could basically do 1B exactly like this with iterate, but we were actually looking into scan left, because scan left, whereas if we look at the API documentation, first of all, how do we find out what methods there are in the iterator object itself? And as I mentioned, so when you visit this page in the API documentation, these are the methods that you have for iterator instances, but we're looking for a companion, for a method in the companion object iterator itself, and I mentioned this so you can see kind of a darker circle behind this medium blue circle. So if you actually follow that link, then you see the object iterator, so that's the companion object, and there you see things like iterate, where it says creates an infinite iterator that repeatedly applies the given function. So that's what we were looking at. But what does that produce? Well, that produces an iterator, so that would work. That would basically work. But the other method that would work even better is the scan left that I mentioned, right? So if we go back to the instance methods, and we see the scan left, okay. And the nice thing about scan left is that you don't need to worry about the termination part yourself, right? So how we rigged up our own way to propagate the termination of the input. So the beauty, and also the other thing that was kind of complicated about the approach we just looked at, what was complicated about this is the fact that we're actually not iterating over our input, right? We're explicitly invoking has next and next. So wouldn't it be nicer if we took the input lines as our collection? It might be finite, it might be infinite, but we want to take the input lines and then iterate over that and somehow express, well, for each input line that we actually get, we'll do some kind of transformation like this F, but it will be simpler because the method scanLeft that we're hoping to use will take care of the situation of the iterator terminating. So That's why this becomes simpler when we use the scan left. So what I'm trying to clarify here is scan left works on an iterator, not out of a vacuum, right? So in other words, let me show you the difference again. So iterate works from nothing, meaning it's a method inside the iterator companion object. So it's like a static method, like a factory method, where we don't need an action instance to start. So if we say iterator iterate 0, and then the function is taking the old x and then returning x plus 1, which is equivalent to saying underscore plus 1, right? If this is our iterator, is this finite or infinite? It's infinite, right? But you also saw that we started this iterator without already having an iterator. So this is a way of creating new iterators from scratch. And here we could say, for example, res7 take while, and say, for example, less than 10, something like that, right? So that's now a finite iterator, and we can see by saying res7 toList, right? So if you use toList on an infinite iterator, that'll be an infinite loop, and you get some kind of overflow. But here, let's see what's going on here. Well, something's interesting, okay. That wasn't supposed to happen. Oh, I know. You know what I did wrong? Does anyone see what I just did wrong? I used res7 instead of res8. Exactly. So if I use res8, that's the finite iterator, and that works as intended, right? But why does it just say list 0? Well, because in the previous step, it went to the end of res7, and res8 is connected to res7. So we have to start the thing again. So basically, what we have to do is we have to do this, okay? Then we have to do the take while, the presumably finite prefix depending on our condition. We have to apply that to res11, and now we have to say res12 toList, okay? And here it is, okay? So anyway, this is always illustrative to see how these things work. So this is great. So iterate is a great way to create iterators from scratch. So it's basically a factory method, right? But what if we already have an iterator, which is what we have here? Which is the iterator we already have? The get lines from the input. So wouldn't it be much nicer if instead of creating an iterator from scratch using iterate, but then kind of explicitly tying it to the existing iterator lines, wouldn't it be nicer if we could just start with lines and use an instance method? And that is the scan left. So the scan left is the instance method equivalent of iterate. And if we have an iterator, so I'm going to create this iterator again of the consecutive numbers. So if we have the scan left, so suppose we want to pair the number with the consecutive number. So suppose we want to have each value paired with 1 plus that value, meaning that we'd want 0, 1, 1, 2, 2, 3, and so on. Kind of a silly example, but structurally it's similar because we're doing something with the old value and then returning consecutive values. So the scan left, we could say, well, initially we'll do 0, 0. And then every time we, so here we'd have to use this case syntax to match the tuple, to pattern match the tuple. So, let's see. Well, yeah, let's see. So, or we can do something simpler. So let's do, let's take 0, and then every time we get a value, x, actually we're getting the old value, so old value and the new value, but new is a keyword, so we shouldn't use that. So then we'll say x, and now we'll say old plus x times x. So what is going to happen here? So we'll get, so like the iterate, we'll start with value 0. And then for every subsequent value, we're going to, for every subsequent value from the iterator, it'll take our old result value and our next item from the source iterator, res14, and the new result will be old plus x squared. And then it'll continue that, and it'll say the old, that most recent result plus the new item squared, and so on. Okay? So this will be basically 0 squared plus 1 squared plus 2 squared, and so on. That'll be the final result with all the intermediate results. So in that sense, this is a general loop construct where you're looping over an iterator, and you're getting, instead of just a very final result of the loop, you're getting all the intermediate results as well. And of course, if the iteration is finite, then the last one of the intermediate results is the final result, right? So it's just like saying for I, or let's say initialize I to 0, and then while or initialize sum to 0, and then while there is input, add the number you're reading, convert it to an int, to sum, and then keep going, right? So if you're only printing sum at the end, that's just the final result. But if you're printing sum during each iteration, that gives you the intermediate results also, and the scan left gives you exactly that. Okay? So here, what we're expecting is summing up all of these squares. So let's try that. And this is, again, a non-empty iterator because we're not pulling items from it yet. But the question is res15 finite or infinite? It's still infinite because res14 is infinite, right? So what we'd have to do is something like res15 take the first 5, for example. And then we can look at that. So we can convert that to a list or sequence. Okay. So this is interesting. It's a little unexpected because it somehow didn't actually produce all the values. So we might have to say to list, and then it'll actually produce the values. So there is a little bit of a difference because sequence is a little more abstract than list. So list is an implementation type. So list is like linked list in Java, and sequence is like list in Java, like the list interface. Okay? So what did we see here? Well, we got the 0, then we got we read a 0 from the underlying source iterator, which is 0, 1, 2, 3, 4, 5, and so on. So we got the first 0 value, squared that, and added it to the total. Then we got a 1 squared, add that to the total, and this is the total, right? Then we got the 2 squared that and added to the total, so 1 plus 4 is 5. The next value we read was 3 squared that, added to the 5, and that gives us the 14, and so on, okay? So this is a way to express something that you would normally express using some kind of imperative loop in a very nice, clean, functional way, but in such a way that you're getting these, all of the intermediate results. And it handles finite or infinite situations in such a way that you can control later whether you want to keep pulling values from it or whether you want to terminate, right? Because the iterator gives the control to the client that decides whether to try to get more items from the iterator using next. Okay. So any questions so far? So it boils down to this, okay? It really boils, for the purpose of your project, all you have to do is, of course, all is quite a lot, of course. So, but what you have to do is define a suitable argument function for scanleft that where x is the successive number that you're reading, right? And old is everything you kind of need to carry over, which includes, for example, the queue in which you're storing the items. Okay. So your argument function here will, of course, be a lot more involved. So it will contain all of that logic for computing the stats. So old will have to be basically the most recent stats for the current item plus what the queue looks like after you've processed that item.
Would the queue be a immutable queue?
Right. In 1B, it would have to be an immutable queue. So in 1B, the only thing you're allowed, so you're not allowed to use any mutable structures or variables other than technically the input iterator, right? Because the iterators are stateful, but they hide the state very nicely. So that's what we discussed on Slack. So the idea is to have an iterator representing the input, because there's really no way around that, because you have to have a way to represent how far you are along the process of consuming your input. And then you produce an output iterator. So those are technically mutable or stateful structures because they represent positions in an iteration. But they're very simple yet very powerful. But everything else, like these auxiliary structures like the queue, has to be immutable. Okay. So again, a reminder. So this is not modular, right? Because everything is just in this one piece, and then we're just printing stuff. But you can see that it is almost modular, because instead of iterating over results and printing its values, we could have expressed some assertions on the values, right? So in other words, this is already modular or modular ready, right? So, and then you can see the modularized versions here, so it makes everything a lot simpler in the sense that your run method, now the key difference, so instead of returning unit, this returns the resulting iterator, and therefore you don't need this slightly complicated observer pattern anymore. You just decide, if I'm running it as a main, well, I take that result iterator and print it, like the simple version we just looked at. Or if you want to test, then you just express some assertions on those resulting values. Okay? So here we're using scanleft, but then keep in mind that the scanleft for iterator is defective in the Scala library. And that's why you have to use either the one up there, scanleft using iterate, right? So this is like the simple version where we used iterate, or you could just use this version, which is more complicated. But you'd want to basically copy one of these instead of just using scanleft on the input iterator, because that one is messed up and it'll prompt you for a value even before it produces the initial value, which it's supposed to release immediately. Okay, so as I said, I reported as a bug, and they acknowledged it, and someone already issued a pull request with a nicer, more explicitly state-based implementation than this one, which is slightly messy. Right, so I don't really recommend this one. I'd recommend this one because it uses the technique of using iterate to create an iterator from scratch, but then base that on the source iterator it, which is this argument here, right? And it's just like the more special case where it is the input lines, but here it could be any iterator of item type or element type T, right? So I recommend you just literally incorporate, this code in your solution, and then express your Project 1B solution in this style. And the challenge is to define the right method with which which you pass as the second argument to scanleft. Okay. We see here how we're iterating over the input lines. So in the future, it'll work out of the box without the need to define our own scanleft. So again, the devil's in the details, as they say. So your equivalent to accumulate count will be much more complicated and will involve managing the queue and then dealing with the different window sizes, producing the stats, and so on. But it's going to be essentially of this form, right? Okay. Any final questions, comments about 1B? Okay. Yeah.
What is the section number for the business resolution?
Oh yeah, 321, right? So let's see, right here. Yep. 321 console applications in Scala. Yeah, and that'll work nicely. You just have to make sure you, let's say if you have a main, so there should be a main somewhere here, like here. You just register that handler here, before you start reading input. That maybe that's the important thing.
Okay, so before, just like at the top of the...
At the very top of main, that's where you want to register that, and it should work then. Sure. Okay. So let's now come back to our discussion of custom-defined algebraic data types. And you're, of course, working on this. You're very familiar with these things. I'm just trying to remind you repeatedly that this is something you've been doing already, like the shapes and similar kinds of tree-like domain models based on a combination of composite and decorator patterns, right? You've been doing this quite a bit. So what you're getting here when doing it in a language like Scala is you're getting the help of these case classes, which make most things much simpler, right, which some of you have already observed. So, for example, case classes give you a structural equality method that works as intended. And tied to that is the ability to use these things in pattern matching. So there's also a reasonable two-string method. So all of the stuff that, even for simple domain objects in Java, you'd have to define manually or explicitly, you get those things defined for you when you use case classes. And then you get pattern matching, which, what does pattern matching really give you? Because you could work with instances of case classes without pattern matching, but then you would have to drill into them, using some kind of path with my object dot instance variable, and expressing things like tests or even any kind of recursive behavior would be much more tedious. So pattern matching gives you the conciseness because it combines basically a case distinction, like a switch, with the structural decomposition of an incoming argument in conjunction with binding pieces of that incoming structure to variables, right? That's what you're getting. So when you look at, let's say, the simple org charts example, right? So there's a size behavior. So your shapes behavior is similar to this one. But basically, you're getting an incoming person node, and here you're ignoring the actual name of the person. You just say, okay, the size is 1. And then if it's an org unit, you're ignoring the name of that org unit, but you're matching the children as 0 or more items, so as a sequence. And then you're going to say something like adding up the sizes of the children, right? But the pattern matching part is where here you're taking a structure and then doing a case distinction based on the structure and breaking down the structure and binding variable names to pieces of the structure. So that makes things like recursive behaviors much more concise in the way you're expressing them. But the algorithms you're already very familiar with. So it's always the same story, and that's something we're going to actually drill into a little bit. Starting, we're kind of starting that already. Oh, I was like off by a few lines. The size is up here, right? So what you're doing is you're saying, well, add up, so just conceptually, to compute the size of a composite node, like org unit. What do? Well, you add up the sizes of the children, and that's what we're expressing right there. So elaborating a little more, so take each child, compute the size thereof. That's what map does. Right? Map takes a collection and uniformly applies some function to each item in the collection. So the collection here is children, and the function we're applying to each child is the behavior itself, recursively. Right? So you're also familiar with this, but when you do it in a visitor style, it looks more complicated. Here it looks more simple. So now what do we have? So we start with the children. We want the sizes of the children, and then what do we want? Well, we want to add up those sizes. And there is a method in the collections API, so that's why I recommend it. Always look at the API documentation for sequence. Always have that up when you're doing this kind of stuff. That's how you know that there are things like max or sum. You don't have to redo those, right? So that's where the height comes from, right? You're doing, or already did a height, and yeah, that's a detail. Like, does it start at 0 or does it start at 1? The reason I slightly prefer the height of a leaf to be defined as 1 is that in that way the height of an empty tree is 0 as opposed to -1, which seems to make less sense. You know, that's a cosmetic issue. It's not a big deal, you know, as long as you're consistent between your behavior and your tests, it's fine. Okay? But so the recurring theme is when you express recursive behaviors, you take the children of the current node and then you typically apply the behavior on one or more of those children. And then you do something with those partial results, and then you give the result for the current node. What you never do is you never do a case distinction on specific children. That is almost always wrong, right? The case distinction happens only at the top level, right? But never inside the body, because when you're doing it recursively, you're coming back here, and you're doing the case distinction. Does that make sense? So if you're finding yourself doing case distinction on specific children, let's say inside of group or inside of location, then you're most likely making it much more complicated than it needs to be. The case distinction happens at the very top level of the recursive behavior. Okay. So any questions about 2A at this point? So is everybody confident that you'll be able to finish 2A by Friday? Really, you know, again, 2A is pretty much exactly the same as your Android Java version minus the Android, plus maybe a couple of things, but also minus the Polygon and some of those things. Yep.
Is 1B also due on Friday?
No, 1B is due tomorrow. Right, unless, I mean, who is confident that you'll be able to finish 1B by tomorrow? So is 1B the bigger problem than 2A? Oh, okay. All right. Yeah, then we'll have to manage that accordingly. I mean, when no one's confident that you'll finish 1B by tomorrow, you know, then that deadline is kind of ineffective, right? So let's do this then. So who is confident that, you know, I'm trying to figure out what will work best. Who here is confident that you'll be able to finish 2A by tomorrow night? Not too many either. Okay. Who is confident that you'll be able to finish 2A by Friday? Most. Okay. Okay, that's more encouraging. Okay. So let's, yeah, I mean, if no one's confident that you'll be able to make enough progress on 1B by tomorrow, there's really no point in leaving that deadline as is. So we're definitely postponing that until Friday, okay? But what you need to do is work with me and John and also talk to each other at the conceptual level, right? Without looking at each other's code, you know, but talking about approaches and techniques at the conceptual level to get this done. So let's now focus. Let's do this. let me ask one more time, is there any remaining questions about 2A right now that I should address here? And then we'll cycle back to 1B, and discuss that in more detail. So any questions, comments on 2A? Or is everybody reasonably confident now that you'll be able to make progress? I mean, the key thing is, for example, to use the pattern matching effectively to understand how the domain model represents shapes, groups of shapes, etc. Right? That is a key piece. And then really the one insight I really wanted you to get out of this kind of project is, so let's go through this briefly. Let's do the height method here. What method will we need to apply on, what behavior do we need to apply to each child first? I mean, what's the general approach? How do we get the height? So let's say we have the root here, we have different subtrees. How do we get the height of the whole tree? What is the key? Well, traversing, maybe at some level it is a traversal, right? But again, we want to look only at what we have, and we want to look at our children as black boxes. Okay? What do I mean by this? So let's look at size again. So what is the size of the node? And now let me make a little drawing. Okay? So today I have my toolbox here. So let's do a little drawing. So here's a root, and then here's some subtrees. Some are big, some are small. Okay. Okay. What is the size of the whole tree? Well, okay, you could say, yes, I got to count all of the individual shapes in all of these trees, right? But that's very conceptual. That's not operationalizable quite yet. So we already have it here. So this tree has 4 children. So each of these 4 children has a size. So hypothetically, size here, okay. So hypothetically, the sizes are 3, 7, 1, and 4. So then the size of this one would be adding up these sizes, right? And that's what we do. But so the key piece is that we're not actually explicitly going in here at the level of the group or the composite branch, group, organization unit, or whatever. What we're doing is we're saying something like, and just look at your code of your Java solution. You're saying something like, for each child, compute the size of that child, right, and add it to the sum. Isn't that what you're doing in your Java solution? Right. So that's just a way to express the same thing without an explicit loop in a functional way. So, and without specifying that you have to visit the children in a particular order, because it doesn't matter, right? So what we're doing here is basically the map means for each child, compute the size of that child, and then take all of those sizes and add them up. Okay. What do we need to do here then? So let's suppose these are the heights. So if the heights of the children are 3, 7, 1, and 4, what is then the height of the whole tree?
8.
Right. How did you get the 8?
1 plus 7.
And why did you choose the 7?
The largest one.
Right, largest one. How do you express that programmatically? So there's a simple way and a complicated way. Complicated is look at each one. Whenever you find one that's greater than largest one you've seen so far, and then that becomes the largest one. Or you could make it simple, like you use sum up here, you use max, right, on a collection. So in other words, what you're going to have here for height will look almost the same as what you have up there for size, where there are those two steps. One is apply the behavior recursively to the children, so then you get these partial results for each child. And then you have to combine them in the right way. So up there, the right way was adding them. Down here, the right way might be just selecting the max. And then, in this case, well, adding one more because you want to take into account that you're looking at another node as the root. Does that make sense? Does this help? Yeah, I'm really trying to help. I'm not trying to make things complicated. So did anyone have a question about the bounding box, or was that part okay? Even for the bounding box, this idea of using map on the children will help you. You want all of the bounding boxes for the children, and then you look at those and you got to get like the values lying the furthest outside, right? And it's very similar to height in that sense, except you're looking at these locations and rectangle values. All right. Well, I know I have appointments with some of you throughout the day, so I'm going to head over there shortly. And otherwise, so I will also announce the decision to postpone the deadline for 1B as well. But the key point for 1B is make sure you use the iterator's example as your guide and follow that closely. It's really not that complicated once you realize that you need to focus on that function that you're plugging into scanleft, and you realize what scanleft does for you, which is quite a bit, but the details, like how do you get from the previous state of the queue to the new queue after processing the next item. It's really about that, which is really a way of saying it's a non-imperative version of the loop body. Okay, so with that, lots of success and talk to you soon.